Welcome back, guys. This is section 2.8, which is related to the hexadecimal numbers. So what are basically the hexadecimal numbers, what are their benefits, and where can we use them? Okay, so previously we have seen that the binary numbers which we have 1010, let's say this is basically a binary number. So this is basically the 4-bit binary number. Okay, and it is very easy to represent it by using these 4 bits. But if we have more bits like this one, like we can see that in computer systems we usually have the integers, 8-bit integers. Okay, similarly int 16, int 32, okay, int 64 as well. Okay, so what is this? In int 8 we have 8-bit integer, we have 16-bit integer in int 16. Okay, similarly in int 32 we have 32 bits, and in int 64 we have 64 bits integer. Okay, so it is very difficult for us to represent all those by using the bits. Okay, so suppose if we have a bit like here 101101110011. Okay, this is basically these are basically the bits. So we don't know that how many number of bits are here, but it is very difficult for us to represent them in the binary form if we have more than 4 bits or 8 bits. So if we have 16 bits, so it is also very difficult for us to represent them by using these ones and zeros. So therefore another system has been introduced. What it does is that it takes 4 bits, okay, and convert it to a single hex code. That is basically called the hexadecimal number. Okay, so that is basically the underlying concept, that why does hexadecimal numbers are used. Because in hexadecimal numbers each bit here we have is basically consist of 4 bits. Okay, so in computer system you would usually have seen that many codes are written like 0x54 ACD05, like this one. Okay, so what does this x means? This x basically represents the hexadecimal number, and this is basically the hexadecimal code. Okay, so this is basically the code which is the hexadecimal equivalent of any number which the computer has to show us. Okay, so that is the underlying concept, that why hexadecimal numbers are used in the computer systems and computer engineering. Okay, so we will start to solve the questions in our upcoming video. So today we have discussed that what are the benefits of using the hexadecimal numbers. Thank you so much, and I will see you soon. So in previous video we have seen the benefits of using the hexadecimal numbers and why we use the hexadecimal numbers in our computer system and binary number system. Okay, so today we are given a question in which we have to convert each hexadecimal number to binary. Okay, so before it we have to see that how a binary number can be converted to the hexadecimal, or hexadecimal number can be converted to the binary number. Okay, so as the name says that it is basically the hexadecimal number. So hexadecimal means 16. Okay, so therefore hexadecimal number system basically consists of 16 numbers which ranges from 0 to 15, okay, in decimal, while this 15 in hexadecimal is called f. Okay, so this is basically the range of a hexadecimal number. Okay, so this is basically the concept behind the hexadecimal number, and in order to convert any number to the hexadecimal number we have a table which can be written here like so. That is basically the table in which we have different numbers. So this is first of all 0 in decimal. In binary, as we have 16 numbers, so to represent 16 numbers we should have at least 4 bits. Okay, so therefore the binary number we will see here will be consist of 4 bits. Okay, and in hexadecimal it is 0. Okay, so 0 0 0 0 and all these up to 9, these will be similar as that of the decimal, but after 9 the decimal numbers will be the combination of the numbers from 0 to 9, while here we will have A, then B, C, D, E and F. Okay, so therefore I have told you that these starts from 0 and ends at what? Ends at F. Okay, so in order to convert any hexadecimal number to the decimal number, what we have to do, so suppose we have here 46 in the hexadecimal number. So what we have to do, first of all we have to see the hexadecimal equivalent of 6, okay, which is at the right side of my number. So the hexadecimal equivalent of number, my number is what? That is 6. So 6 is 0110. Okay, so let me write 0110. Okay, this is the binary equivalent of this hexadecimal number. Similarly, in order to convert this 4, what we have to see, we have to see the binary equivalent of this hexadecimal number again. So what is this? Let me see here. So this is now here, this is 0100. So let me write here 0100. Okay, so now refining it, it will be 0100 0110, and this is the binary equivalent of my number, that is in hexadecimal 46 16. Okay, so that is, sorry, this is was basically 16. So this is the conversion of my number to the hexadecimal level. Similarly, in order to convert the part B, which is 54 16, okay, first we have to see that what is this 4 equal to, that is again 0100. Okay, and 5 equal to 0101. So 0 1 0 and 1. So that is the binary equivalent of 54 in hexadecimal. Okay, so now let me remove them and start solving other questions. So part C here is B4 16. Okay, similarly following the same procedure, the 4 here will be how much, that is again 0100. Okay, 0100, and B is how much, that is B, which is 1011. Okay, so 1011. So that is the binary equivalent of the number which is here. Okay, part D here is 1A3 in 16. Okay, so now we can see that we have 3 digits. So first of all, writing the equivalent of 3, that is here. So that is 0011 0011. Okay, the equivalent of A is how much, that is 1010. So 1010. Okay, and the last one here is 1, which is here. So 0001. Okay, so 000 and 1, while this one is this one. Okay, so we can see that here we have converted them in the parts of 4s, in 4 parts, which are basically 1010. This one is here as well. Okay, so each bit here is, this is 1, this is 8, this is 3. So that is the hexadecimal equivalent of the number. Similarly, we have here, let me remove it again. Okay, this is part E, and it is here FA16. Okay, so A is here, we can see that A is 1010 1010. Okay, and F is here. Okay, this is 4 times 1, so 1 1 1 1. Okay, so this is here. Okay, so we can see that this one is here while this one is here. So that is the binary equivalent of my number. Similarly, part F of my question, A, B, C in 16. Again, at 3 digits we have here in the hexadecimal number. Now writing the equivalent of C here. The equivalent of C is here, 1100. Let me use this green color. So 1100 for this C. Okay, for B it is 1011. Here we can see that 1011. So for B 1011. Okay, and for A we can see that for A it is 1010. Okay, so taking it and writing it here, so 1010. Okay, so we can see that this is a number, this is another 4-bit number, and the last one is here, this one. So that is basically the binary equivalent of my number. Okay, so we can very easily see that here the 12 bits are very easily shown by using the 3 hex codes. Okay, so that is the efficiency of my hexadecimal number. So the last one here is, what is the last one? In the last one we have 4 digits which are A, B, C, D. Okay, so we have here A, B, C, D, 16. Okay, so therefore now using the same procedure in which the D, first of all we have to write the codes of D, then C, then B, and at the end we have to write A. Okay, so let me write them here. So initially the code for D is how much? That is here 1101. So 1101 here. Okay, so that is for D. For C we have here 1100. So here we have 1100. Okay, so this is for this one, these 4 bits are for this, while these 4 bits are for D. Okay, for B we have here, we can see that this is for B, so 1011. So 1011, this is for this B, and for A we have this 1010. Okay, so this is for this number. So we can see that here we have these 16 bits which are very easily represented by these 4 codes which are in hexadecimal numbers. Okay, so that is for today, in which we have discussed the hexadecimal numbers and how does a certain hexadecimal number can be converted to its binary equivalent. From the next video we will try to solve some more questions which will be related to the hexadecimal numbers. So till then, take care of yourself and I will see you soon. Welcome back guys. So this is question number 38 of section 2.8, in which we have to convert each binary number to the hexadecimal number. Okay, so in previous question we have seen that how to convert a hexadecimal number to its binary equivalent. So today we will see that how to convert a binary number to the hexadecimal number. Okay, so we are again going to use the same table which we have previously used. Okay, so here all the binary codes are written, their decimal equivalent is also written here in the leftmost column. Okay, and the equivalent hexadecimal numbers are also mentioned here in the rightmost column. So let me start it from part A. So here we have these all ones, so this is basically a 4-bit number. So from this table we can see that in binary this all ones is equal to F, so therefore the hex equivalent of it is F, and that is in 6, while this was a binary number. Okay, so that is the answer of part 1. For part B we have 1011. Okay, so in this table we can see that 1011 is how much? That is B, so B is B16. Okay, so that is the answer of part B. For part C we can see that here we have 1 1 1 2 3 4 5 5 ones. Okay, so 1 2 3 4 5, we have 5 bits here. So what we have to do in this situation, what we have to do, we have to combine the 4 bits in each of the number, and we will start from the LSB. Here we can see that it is the LSB, while the leftmost bit will be the MSB, which stands for the most significant bit. Okay, so we can see that here we have these 4 bits and these are now mentioned here. So 1111, this is the F, But what about this one? This is 1, so we don't have anything here. So therefore, we ourselves should have to put zeros here. So after putting it, we will see that it will become a 4-bit number. So now this 4-bit number will give me a number which is 0001. So that is equal to 1 here. Okay, so that would be the 1F in the hexadecimal number. So that is the answer of part C. So in part D, we can see that here we have how many bits. So here these 4, okay, and the last 4, because this is an 8-bit number. So we can see that 1010 is how much? That is 1010. So that is A. Okay, similarly this is also 1010, so this is also A. So that is AA16. That's it. That is the hexadecimal equivalent of part D. Similarly, in part E of my question, we will start to do it from here again. So that is a 4-bit number. Again, this is a 4-bit number because in total this is the multiple of 4, because in total number of bits here are 8. So therefore 1100 is here equivalent to C. Okay, so we can see that 1100 is C. Okay, and 1010 is how much? That is A. So that is the hexadecimal equivalent of AC, and this is the answer, while this one is here. The last one here is this one. So let me start here. So this is now this one, and the last one here is here. So now 1011 is how much? So 1011, this one. Okay, 1011 is B, this is B, and 1011 again B. Okay, so that is the hexadecimal equivalent of it. Okay, so that's it for today, in which we have seen that how easy it is to convert any binary number to the hexadecimal number if we have this table. Okay, so here in this table we have seen the benefits of converting any binary number to the hexadecimal, similarly any decimal number to the hexadecimal number as well. Okay, so that's it for today, in which we have seen the benefits of it, and in our upcoming video we will see some more questions. Till then, take care of yourself. So welcome back, guys. Today we are going to talk about the hexadecimal to decimal conversion. Okay, so here we have different parts of this question in which we are asked to convert each hexadecimal number to the decimal number. Okay, so the first one here is 42 in hexadecimal. Okay, so what we have to do, our approach will be to first convert it to the binary. Okay, and from binary we will convert it to the decimal equivalent. Okay, so here will be our approach. So as we have again this table, so why would we use this table? Because of converting this hexadecimal to the binary one. Okay, so what we have to do, we have to write the binary equivalent of 42. So let me write it here. This is 42. Okay, so the binary equivalent of 42 will be, as this is the hexadecimal number, so writing the equivalent of 2 here, what it would be, we can see that the equivalent of 2 is, this is the hexadecimal number, and its equivalent, binary equivalent, it is here. So it will be 0010. Okay, so that is the binary equivalent of it. Similarly, the binary equivalent of 4 will be how much? We can see that this is 4 and its equivalent is here. So 0100. Okay, so writing here 0100. So that is the binary equivalent of this 42. Okay, what we have to do now, we have to convert it to the decimal. Okay, so converting it to the decimal, what we have to do, we have to use the same procedure which we had previously used. So here it will be 2021 22, okay, 23, 24, 25, 26 and 27. Okay, so we can see that only 2 raised power 6 multiplied by 1 plus 2 raised power 1, these two are ones here while others are zeros. So 2 raised power 6 is how much? That is 64. Okay, and this is how much? This is 2. Okay, so the decimal equivalent of it is 66 with the base 10. Okay, so the decimal equivalent of 42 is 66 with the base of 10. Okay, so that is the procedure we can follow for all the other terms as well. So let me start part B here. So to start part B here, what we have to do, let me clear it. Okay, and here this one as well. Okay, so now this 64 in hex, what we have to do, first we have to find the binary equivalent of it. So binary equivalent of 4 is this one. This is 0 0 1 0 0. So 0 1 0 0. Okay, and the binary equivalent of 6 is how much? That is here, this is the hex, and 0 1 1 0. So 0 1 1 0. Okay, so that is the binary equivalent of 64. Okay, we can write here, this is the binary. Okay, and in order to write the decimal equivalent of it, what we have to do, again we have to write here 20 21 22 23 24 25 26 27. Okay, converting it to the decimal, what we will get here, only this 2 raised power 2, this is 1, while this 1 2 raised power 5 is 1, and this 2 raised power 6 is 1. All the other terms are 0 here. So now writing them here, 4 plus 2 raised power 5 is 32. Okay, and this 2 raised power 6 is 64. So 64 plus 32, that is 96. 96 plus 4 is 100. Okay, and this 100 is in decimal, so that is the decimal equivalent of my number, which is now here. Okay, so that is the procedure of finding the equivalent decimal number of any hexadecimal number. Okay, similarly, now removing it, and for part C of my question, what we have to do, that is 2b16. Okay, again the binary equivalent of these will be, the first one here is b, so b is, we can see that this is b, so that is 1011 1011, and the binary equivalent of 2, we can see that this is 0010. Okay, so that is the binary equivalent of it. Now converting it to the decimal, so that is 2021 22 23 24 25 26 27. Okay, so that is what, that is the binary. Okay, so now here we can see that only 2 raised power 0 plus 2 raised power 1, 2 raised power 3, and 2 raised power 5, these terms are multiplied with this 1 and will give me the values whatever weight these would have. Okay, so we can see that these are the values. So now it would be 1 plus 2 plus 8 plus 32. Okay, so now writing them, what I will get, 32 plus 8 is 40, 40 plus 3 is 43. Okay, so that is what, that is the decimal equivalent of my number. So we can see that the decimal equivalent of 2b is 43d. All the other terms will also remain same, and the procedure of finding their equivalent will be just like here we have done here. Okay, so this is the solution of part C. Similar will happen with this 4d, in which first we have to write the binary equivalent of 4 and then d, and then converting it to the decimal will give us the decimal equivalent of it. Okay, similarly here this ff, we can see that we can see that every f is composed of the 4 bits, 4 1 bits in its binary equivalent. So therefore this ff will contain 8 ones. Okay, so okay, we have to convert them, and we will see that we will get some numbers in the decimal. Okay, so it will be easier to convert them into the decimal equivalent. Similarly, we will do it for this one as well, where b and c are two numbers. So c is equivalent to what, that is 1100. Okay, and b is equivalent to what, that is 1010. 1 1. Okay, then we will convert it to the decimal from this binary number, and we will see that the equivalent will be the decimal equivalent of these number. Okay, so the last two are basically composed of these three hexadecimal codes. Okay, and it would be somehow different to calculate their results, so we will do it in our upcoming video. Till then, practice all the stuff which we have covered today, and I will see you with some more stuff in our upcoming video. Thank you so much, and I will see you soon. Welcome back, guys. So previously we have seen the conversion of the two-digit hexadecimal number to the decimal one, and we were left with these G and H parts. Okay, so let us first find the decimal equivalent of this G part. So G is 6, F and 1. Okay, so as this is a hexadecimal number, what we have to do, we have to find the binary equivalent of these. So 1 is, we can see that this is here. Okay, so it would be 0 0 0 1. Okay, F is how much? That is 4 times 1. Okay, so 1 1 1, and this is 6. We can see that this is the binary equivalent of F, while 6 is how much? That is 0 1 1 0. Okay, so 0 1 1 0. Okay, so these are here. Now as we have found them out, what we have to do, what is the next step here? We have to find the decimal equivalent of this binary number. So this would be 0 1 2 3 4 5 6 7 8 9 10 11. Okay, so from here we can see that all the numbers which are multiplied with these ones here, so here the weights which has a multiplicative factor of 1 will be 20. Okay, similarly adding them, this 2 raised to power 4. Okay, this 2 raised to power 5, this one 2 raised to power 6. Okay, 2 raised to power 7. Okay, so we can see that it is this one, this one is also this one, this one, this one. Well, now here 2 raised to power 9 and 2 raised to power 10. So 2 raised to power 9 plus 2 raised to power 10. Okay, so now adding them, we will get our number. So in order to add them, what we have to do, this is 1, this is 16. Okay, this is 32, this is 64, this is 128. Okay, how much is this? This is 512. Okay, and this is 1024. So in order to add them, you may use a calculator. So let us use a calculator here. So here, in order to add them, what we will do, 1 plus 16 plus 32 plus 64 plus 128 plus 512 plus 1024. Okay, so what we will get here, 1777. So 1777, that is the decimal equivalent of my number here. So what was that? This was basically the binary number. Okay, this was a hexadecimal, and now at the end we have got the decimal equivalent of my number. Okay, so that is about part G of my question. Similarly, we can also do it for part H as well. So let me do it for part H. Okay, so part H is A, B, C. Okay, the equivalent of C is here. We can see that that is 1100. Okay, the equivalent of B is 1011, 1011, and the equivalent of A is here, that is 1010, 1010. And now multiplying them with the weights it has, so we can see here that this is the hexadecimal This is the binary equivalent of it, and now from this binary we have to find the decimal equivalent. So that is 2021, 22, 23, 24, 25, 26, 27, 28, 29, 210, 211. Okay, so now getting all the weights with which the multiplicative factor is 1, what we will get here, it will be 2 raised to power 2 plus 2 raised to power 3 plus 2 raised to power 4 plus 2 raised to power 5. Okay, so after 8 here it will be 2 raised to power 7. Okay, so after 8 this one 2 raised to power 9. Okay, and then 2 raised to power 11. What we have to do, we have to add them. So here it will be 4 plus 8 plus 16 plus 32. Okay, so 2 raised to power 7 is how much? So let me calculate it. 2 raised to power 7 is 128 plus this is 512. Okay, and 2 raised to power 11 is 2048. Now adding them together, what I will get? So let me add them. 2048 plus 512 plus 128 plus 32 plus 16 plus 8 plus 4. Okay, so what I will get here, I will get 2748. So 2748 is the decimal equivalent of my number. Okay, so that is the decimal equivalent of number. So that's it for today, in which we have seen that how to convert a 3-digit hexadecimal code to the decimal equivalent. Okay, so I will see you with some more interesting questions in our upcoming video. Till then, take care of yourself and I will see you soon. Welcome back, guys. So in previous section we have seen that how to convert any hexadecimal number to its decimal equivalent. Okay, so in that video what we have done is that first we had a hexadecimal number. Okay, we have converted it to the binary one. Okay, and from a binary number what we have done, we have converted it to a decimal equivalent. Okay, so now in this question we have some decimal numbers, and from the decimal we have to find the hexadecimal equivalent of these numbers. Okay, so what will be the procedure here? So the procedure here will remain same. While here we have a decimal number, first of all we have to find the binary equivalent of it, and from the binary we have to find the hexadecimal. Okay, so the overall procedure will remain same. So here the first question we have is this 10. Okay, and we can see that the binary equivalent of it is how much. We can use this table here as well. So the binary equivalent of 10 is 1010. Okay, so the hex equivalent of it is also given here, and that is a. So that is the hex equivalent of my number 10 here. Okay, so that is in base 10, this is in base 2, and this is in base 16. Similarly, we have this 15, this in base 10. So the binary equivalent of it is here. It is also given here. The binary equivalent of it is 1111. Okay, in binary, and we can see that the hex equivalent of it is also given here, and that is F16. So these are here. We have easier parts, and we have seen that how to find their equivalent here. So what we have here, this part C. So in solving part C, what we have to do, let me remove it. Okay, in solving 32, what we have to do, first we have to convert it to its binary equivalent. So in binary equivalent we will have 20, 21, 22, 23, 24, 25, 26 and 27. We have to use the sum of the products rule. So here 32, the number here is this 2 raised to the power 5 is 32. Okay, so we can write here 1 while others 1 will remain zeros. Okay, so the binary equivalent of it is this 2 raised to the power 5. So, okay, so all the others will remain 0. So therefore what we have to do, we have to use here this is binary while this is another binary. Okay, so here the 0 0 equivalent here, this is 0, while here 0 0 1 0 is equivalent to how much? That is now 2. Okay, so we can see that this is 2. So therefore the hex equivalent of this 32 is 20 in hex. Okay, so that is the hexadecimal equivalent of my number, which is 32 here, that is in decimal, while this one here we obtained is in binary. Okay, so that is the procedure by using which we can convert any decimal number to the binary equivalent. So another one here is this part D. So let me solve part D here. So in part D we can see that that is 54 in decimal. Okay, so converting it to the binary equivalent, what we have here, we have here 2 raised to the power 5 is 32. So let me write it here, 132 plus 16 is how much? That is 48, and 2 are left, so this is 1. So all others will remain 0 here. Okay, and making all other 0, what we can do here now, taking groups of 4s here, so 4 bits group will give me here, this is 00 0010. So 0010 is here equivalent to 2. Okay, so that is 2, and similarly 0011, let me see here, is that 0011 is 3. Okay, so that is 3. So therefore that this was basically the binary equivalent. So from it we have obtained this number, which has given me 32 in hexadecimal. Okay, so we can see that this 32 is the hexadecimal equivalent of my number 54 in decimal. Okay, so that's it for today, in which we have discussed some very easier methods for converting decimal number to their binary equivalents, and from the binary equivalent we have seen that how to convert those binary equivalent to the hexadecimal equivalents. So that's it for today, and see you soon.